We're going to begin by looking at a simple example of using the velocity of a given motion in order to recover the position. So in this example, we have, suppose that r of t is a motion with r of 0, so the position at time 0 being 1, 3, negative 2, and velocity v of t, which is, of course, the derivative of r of t, being equal to t minus cosine t e to the t. Find the position function. This is a quite routine problem. The idea being that the position function will be given as the integral of the velocity. And here one could write actually a definite integral that precisely gives what we want. However, let's work with an indefinite integral. So let's begin by computing the indefinite integral of t minus cosine t e to the t, so as to show how we're going to handle the constant. Because what will happen is that we have t squared over 2 negative sine t e to the t. These are the antiderivatives of the three components. And then instead of putting c1, c2, c3, we put plus a vector c. And now we're going to ask that if we take this expression right here and we plug in t equals 0, then that should give us 1, 3, negative 2. So what does that mean? That means that if I plug in 0, I will get 0 on the first component, 0 on the second component, and 1. And if I add c to it, that should equal to 1, 3, negative 2. And if we solve for c, we will get 1, 3, and negative 3, because we need to change the sign of 0, 0, 1 when we take it over the other side. If we put everything together now, then we have that r of t is equal to t square over 2 negative sine t e to the t plus 1, 3, negative 3. And if we want, we can write it all together as t square over 2 negative sine t e to the t. Oops, I just wanted to distribute the constants. So negative t square over 2 plus 1, negative sine t plus 3, and e to the t minus 3. And that's okay. So now we have the full position function. And please note that in cases like this, you need to have an initial condition. Otherwise, you will be able to find the position up to a constant rather than down to a specific formula. The next thing that I would like to describe is how we find the vector equation for a tangent line to the trajectory of a vector valued function. And here's the interesting observation. We should start actually by asking, what's the interpretation of the velocity vector? what exactly does it signify? So let's say that you're looking at the trajectory of a vector valued function. So this is a motion, right? And let's say that at time t naught, you happen to be here. And the velocity vector is something like this. Now, the velocity vector, as we're going to explain in a second, is geometrically tangent to the trajectory. But there is a very nice interpretation to it, okay, in the realm of mechanics. So first of all, the fact that the motion that you're looking at is described by this vector valued function suggests that there have to be some forces that act upon a moving object for this to be possible. This is simply because of Newton's laws that tell us that if the algebraic sum of forces that act on an object is zero, then this either is a stable or it moves at a uniform speed. So, so there are certain forces that allow the object to have such a curvilinear and possibly not constant speed motion. So imagine that for time t equals to t naught, meaning right here, all forces cease to exist. So it's almost a cartoon-like situation, right? I don't know if you ever saw these cartoons where, one chases another, and then all of a sudden, the ground and everything else disappears from underneath their feet. But imagine something like this. So if there's an engine, it disappears. If there is ground, it disappears. All forces cease to exist. And you ask then, if that happens at some point during the motion, what will happen to the moving object? And the answer is that from that point on, the moving object will just move uniformly. And the vector of that motion is nothing else but the velocity vector. So, and its direction is the tangent that we need. So that means that we have a very nice equation for the tangent to the trajectory of the vector valued function r of t for t equals 0, for t equals t naught. It is going to be, so let's denote it by L of t equal to the position vector r of t naught at time t plus t times the tangent vector. Okay, or if you like, the velocity vector. Let's look at an example. Find a vector equation for the tangent to the trajectory of r of t is equal to t squared negative t cubed for t equals 0. Okay, please pause the recording and try to solve this by applying the formula, but I'll give you a couple of Second, still I do it, and here's the solution. Solution is to simply compute r of 1 and r prime of 1. So what is r of 1? The position vector for time equal to 1. It's going to be 1, 1, negative 1. And what is the velocity, r prime of t? It's going to be 1 to t negative 3t squared, which means that r prime of 1 is going to be 1 to negative 3. Now we have the two vectors that we need for our equation. So the tangent is going to be 1, 1, negative 1 plus t times 1 to negative 3. Now, one should say something interesting, that you're going to get an actual line if and only if the tangent vector that you find is non-zero. And assume that this is going to be the case, but one could ask, what happens when the tangent vector is 0? And this is usually when your motion can do something very, very strange, like having an abrupt change of direction or something along those lines, some cusp, let's say. But this is not going to be of any importance or consequence to us. This is the kind of nice case that we'd like to look at. There's one more thing that we should say here, and that is that to any motion, we can associate the unit tangent. The unit tangent is simply the normalization of the velocity. And so this is going to be a v of t divided by the magnitude of v of t, which is, by the way, the speed, or r prime of t over r, the magnitude of r prime of t. Now, this is a unit vector. We assume, of course, that the velocity here is never 0. And since the magnitude of this is 1, its derivative is going to be perpendicular. And sometimes we take this derivative, we further normalize it. We know that it's normal to the, it's perpendicular to t. And we call it the principal normal. And there is a reason why we call it the principal normal. It's because we're in 3D space, you have this vector t, and you're looking for a very specific vector that actually somehow pertains to the motion and is perpendicular to t. So principal normal. So think about it this way, that here you have your motion. At every point, you have the tangent, the unit tangent, and then you find a vector which is perpendicular to that unit tangent. And pretty much varies nicely, remaining perpendicular to t as you go from point to point. It turns out that anything pertaining to the motion is inside this plane, which is generated by these vectors. This is usually this two-dimensional plane, which is generated by the unit tangent vector t, and the principal normal is oftentimes called the osculated plane. The other interesting thing that one mentioned here is that by looking at the vector t on examining the way that the vector t changes direction in a way that is proportional to the length of the trajectory, one can define the curvature of a curve. We're not going to go down that path, actually. And we will have very little use for the things that we just mentioned. But all I'm trying to indicate here is that that could be a very interesting direction of study. What we're going to do next is look at the notion of arc length. So the idea here is very, very simple. You move together with a vehicle for which the odometer doesn't work. Odometer, what is the odometer? The odometer is the instrument that measures distance. So imagine that this doesn't work. However, the speedometer does work. What is the speedometer? The speedometer is the instrument that measures the speed. Is there any possible way to actually measure the speed, the distance, by just using the speed? And the answer is pretty straightforward. All you need to do is take your motion, subdivide it into very, very small pieces, and multiply the corresponding time with the speed at a randomly chosen point of each piece. The idea is that since the pieces are very small, the speed can be thought of as being uniform, being the same, being constant, in other words. And for such small periods of time, distance is the same as speed times time. So in the case of uniform speed, constant speed, distance is speed times time. So we can approximately compute the distance for each of those pieces at the map, and then pretty much refine the process. What we're doing is actually computing Riemann sums and refining those sums. So the whole process is pretty standard. And thus, what this reveals is that the integral of the speed should give us the distance. So we can come up with the following formula. The length of trajectory of r of t is simply the integral, and I should say here, from time A to time B, is the integral from A to B of the magnitude of the speed. And let's look at the first example. So compute the length of the trajectory of r of t equal to t squared over 2 square root of 2 times t and ln of t from t equals 1 to t equals e. Okay, let's see how we would do that. The idea is to simply implement this formula. To implement this formula, we need to start by computing the derivative of r of t, which is what? It's t square root of 2, 1 over t. And what is the length of this derivative, which is the speed? Square root of t squared plus 2 plus 1 over t squared. So we will need to integrate this function. And this is not some isolated challenge that we're finding here. When we try to find lengths, we will very often come up with these integrals of functions contained inside square roots. And those integrals are not so easy to come up with their antiderivatives, with the antiderivatives of the integrants. But there is this little trick that if we were able to get rid of the square root, then we might be able to come up with a much simpler integrand. The idea is that one of the tricks that we should take into consideration is look at the quantity under the radical. In this case, the quantity under the radical is t squared plus 2 plus 1 over t squared, and try to recognize it as a perfect square. What will come to our help here is the identity a squared plus 2ab plus b squared being equal to a plus b all squared. So look at the present example, for example, and try to identify a and b. And the answer is that a will be simply t and b will be 1 over t. So you have t squared, then you have 1 over t all squared, right? So this is your a squared and the b squared. And what is the number 2 in the middle? It's the same thing as 2 times t times 1 over t. See how everything matches exactly our identity. I'm not saying that this will always be the case. All I'm saying is that keep this trick in mind because it might occur more often than you think it will. And here this will end up being t plus 1 over t all squared. Eventually the square root cancels with the square, giving you t plus 1 over t. And what you need is the integral from 1 to e of t plus 1 over t dt, which is t squared over 2 plus ln of t. I don't need the absolute value because I'm over a positive interval. And this will be e squared over 2 plus ln of v minus 1/2, 1 squared over 2, 1/2, minus ln of 1, which is 0. Ln of e is 1. So this number is 1. This number is 0. And 1 minus 1/2 is 1/2. So the answer here will be e squared plus 1 over 2. That's the length. Okay, very interesting example, one that it's worth pausing the video and do it a few times till you become comfortable with it. Let's do a similar one. You can see one can really play with this theme a lot and come up with quite interesting situations. So take a look at the following example. So find the length of the trajectory of r of t equals e to the t, e to the negative t square root of 2 times t from t equals 0 to t equals t equal to ln of 2, and give the answer in a nice way. Give the answer in the form a over b, where a comma b are natural numbers. So as a fraction, as a nice fraction. So again, I would suggest that you try to pause the video and try to do this problem. And here's the solution. So again, we want to find r prime of t, which will be e to the t minus e to the negative t and square root of 2. The magnitude of this is going to be square root of e to the 2t plus e to the negative 2t plus 2. And now the idea here is that we can rewrite this as e to the t all squared. The number 2 can be written as 2 times e to the t times e to the negative t. And the e to the negative 2t can be written as e to the negative t all squared, square root of that. And this will be square root of e to the t plus e to the negative t all squared. Now we're dropping the square with the square root. And basically we want to find the integral from 0 to ln of 2 of the function that we just ended up with, which is the speed. And the antiderivative for this will be simply e to the t minus e to the negative t from 0 to ln of 2, which will give you e to the ln of 2 minus e to the negative ln of 2 and minus e to the 0 minus e to the negative 0. Now things should clear up here, because e to the 0 is 1, e to the negative 0 is also 1, so the whole thing is 0 right here. And e to the ln of 2 is 2. E to the negative ln of 2 is not negative 2, it's 1/2. Why? Because it's 1 over e to the ln of 2. And the final answer is 2 minus 1/2, which is 3/2. So the final answer is given in the format that the problem asked us for. And that's it. Now, so in some sense, this should let us know that unless you are in a very convenient situation, finding the arc length can be quite a task, or possibly an impossible, might reduce to an impossible algebraic task, an impossible integration task, actually. There's one other very interesting thing that we should add in passing. We're not going to to use it. Remember, for example, I told you before that if we observe the direction of the tangent, how fast it varies, we could define the curvature. How are we going to determine that something varies at a speed which is the reference speed that we would like to look at? And the idea is simple. If r of t, if the speed is always equal to 1 for every t, then we say that r of t is an arc length parameterization for its trajectory. So the question is this: if you give me your random curve, is there an arc length parameterization? And the answer is basically yes. I mean, so say that you start at this point and you have a parameterization. Let's agree that at least you can find one parameterization. So let's call this parameterization R1 of t. A parameterization for the curve. Then you can start measuring the length. So the length with respect to time t is going to be the integral from 0 to t. Now, here I would like to put the speed, but here's a small problem. I don't want to put t again because I have it as the endpoint of integration. So let me just say r1 prime of u du. So this gives us the length of trajectory from 0 to t. So the length becomes a function of t. What we're supposed to do is take t as the inverse function of the length. And then the claim is that r of t, r of s actually, being equal to r1 composed with this L to the negative 1 of s is an arc length parameterization. Truth is that there are not too many arc length parameterizations. I mean, essentially, you have two of them depending on which direction you choose to traverse the curve. In order to understand how this works, let's do an example. Let's do an example. So, example. Find an arc length parameterization for r of t, let's say a helix, right? let's do this. Okay, so what is the length of the trajectory from 0 to t? So it's going to be the magnitude of the derivative, which is what? Negative sine u, cosine u, and 1 du, which is 0 to t. That will be square root of sine square of u plus cosine square of u plus 1. This is 1. So this will be the integral from 0 to t of square root of 2 du, which ends up being a square root of 2 times t. So you see now what happens. S is square root of 2 times t, which means that if we solve for t, we get that it's s over square root of 2. So the idea now is to put R1 of s, the new parameterization, will be the previous one, and we replace t by s over square root of 2. So cosine of s over square root of 2, sine of s over square root of 2, comma s over square root of 2. And this is an arc length parameterization. Actually, verifying that it's an arc length parameterization is done by using the first form of the fundamental theorem of calculus. But what I would like to emphasize here is that unless this relation that we find, the relation of the length with respect to time that we find, is easy to solve for t, you will still face some big challenge of expressing the arc length parameterization explicitly, even though it will always exist. And this process itself shows that the arc length parameterization exists. Finding it is a different story that hinges on how convenient the integrals that one gets in this process are. And that's all. Thanks for watching.